Today, we're going to look at what is arguably the most important concept in AP Physics 1, which is a conservation of momentum. It's just a tremendous tool for solving physics problems. And it's not that hard to understand. So let's get started with it. So please remember that Newton's third law tells us that in order for a force to exist, there must be two objects. A force is an interaction between two objects, and they both feel that force equally in opposite directions. And since force causes acceleration, acceleration changes momentum. Remember what we learned about impulse. It leads to a very remarkable thing, which is this force acting between two objects cannot change the momentum of that two object system. So let's just take a look at this. So let's just say I have two 1 kilogram carts that are connected by a stretch spring between them. Now, I know that spring force varies with displacement, but for right now, let's just pretend it doesn't. Let's just say that this spring is exerting a 4 Newton force. Well, that 4 Newton force acts this way to the right on this object, and it acts to the left on this object. So the force acts between them equally and oppositely, right? So right now, if I look at the momentum of the system before I release them, I have 1 kilogram and it's at rest. So the momentum here is zero. And I have 1 kilogram at rest here. So the momentum here is zero. So when I sum this up, I get a system momentum of zero. Now I release them. And this force acts, let's just say over a time period of 1 second. Let's just pretend it's a constant 4 Newton force acting over 1 second. What that means then is that there's going to be an impulse of 4 Newton seconds or kilogram meters per second on each object. In this case, this object is going to have 4 kilograms meters per second to the right, and this one is going to experience 4 kilogram meters per second to the left. So when I sum their momentums, I get 4 plus -4. I still get zero. The momentum of the system did not change. And when we have a quantity that does not change, that always stays the same, we refer to that as a conservation law. So we have conservation of mechanical energy as long as there's no uh, non-conservative forces acting on a system. And now we have another one, which is conservation of momentum. And the thing about conservation of momentum is there's no ifs, ands, or buts about it. It is always conserved in all interactions. So that gives us a very powerful thing. When we say however much momentum is gained by one object is gained in the negative direction by the other one. So the net momentum of the system is never going to change as a result of an interaction of a force between the two objects. Now, of course, you can have an external force acting on the system. We'll deal with that later in the unit. So let's just do a force versus time graph for this. And again, I'm sorry, I just wanted to keep things simple, so I made it like a uniform change here. So here you go. So if I do a force times time graph on these, remember this area here is going to be the impulse. It'd be force times time. So I start here. What I see is that this force here on A is going to be acting in the positive direction, and I'm going to have an identical force acting in the negative direction on the other one. And when they hit each other, there's no longer going to be any force at all. Well, what's going to happen then is this. If I take this area here, I'm going to say 20 times 1 divided by 2. I get 10 Newton seconds or kilograms meters per second acting on this one. And since it has a mass of 1, it will accelerate to 10 meters per second as a result of this force acting over that time period. But the other one will acquire negative 10. All right. And so they basically, if I look at these two, I have 1 kilogram at 10 and 1 kilogram at -10. And when I sum that up, I get zero. There's no change to the momentum of the system. Now let's change the mass of the objects because then it starts to become a little bit less obvious to most students. So I'm going to do the exact same thing. I have that same spring stretched between them. It's going to apply its force for the same amount of time, but there's going to be a difference. In this case, what's going to happen is this, that 20 times, positive 20 times 1 over 2 still gives me 10. And so it's going to acquire 10 meters per second in the positive direction. But the other one has twice the mass. Since it has twice the mass, the change in velocity is going to be half as much. It's going to be -5. But when I calculate the momentum, you've got it. 1 times 10 is still equal to 2 times -5, which still gives me a system momentum of zero. Momentum was conserved. The force between these two objects cannot change the momentum of the system. Well, now let's look at this one here. I mean, I think a lot of us have we've seen movies in which people fire guns or cannons, and we see this thing called recoil, where the thing that's projecting the object, so like the gun or the cannon, rolls backwards after the shot has happened. And that's because there's equal and opposite forces, Newton's third law. So let's just try this. Do you like my cannon? It was a little bit hard to draw. I kind of like the way I made the barrel this way. Not the best. I'm not the best artist, but I'm still a bit proud of what I can do here with my limited skills and resources. So here you go. I have a frictionless surface of ice. I have a 100 kilogram cannon here, and I have a 1 kilogram cannonball, and they're at rest, right? So the momentum of the system is zero because I have 100 times zero plus I have 1 times zero. So the total momentum of the system is zero, and it's going to stay that way if it's just a result of an interaction between these two. Okay, no outside force is acting. So we fire this. Look at that, that's pretty cool, right? Boom! When it goes off, there's going to be a force of explosion force is going to push in all directions. And so what's going to happen is that same 1,000 newtons of force is going to push the cannonball to the right and the cannon to the left. And it's going to be an equal amount of force acting for an equal amount of time, and I chose the amount of time to make my life easy, 0.1 seconds. So if I say 1,000 times 0.1, I get 100. So there's going to be 100 units of momentum change on this object in the positive direction and 100 units of momentum change on this one in the negative direction. So I'm going to, oops, what did I just do here? Oh, man. Oh, what did I just do? Okay. So if I come here, so what I see now is I've got 100 kilograms, and it's going to be moving backwards at 1 meter per second. So when I multiply those together, I get a momentum of negative 100. And here I have a 1 kilogram object traveling to the right at 100 meters per second. It's got the same momentum in the positive direction. This one has the negative direction. So when I sum that up to find what the momentum of my system is, I get what I started with, zero. That is conservation momentum. See, it's not that hard of a concept. So again, because the change of momentum is going to be the same in both directions, because the same force acts at the same time between the two objects, that leads us to this concept of conservation momentum, which we can express this way. The sum of the initial momenta will equal the sum of the final momenta. In other words, if I sum up all the mass times velocities of the objects before, it will equal the sum of the mass times velocities of all the objects afterwards, provided that no external force act on the system, that these changes in velocity are only a result of forces between the objects which are defined to be part of our system. So let's try this one here, okay? I've got a 1m object at rest and a 1m object with velocity v. So if I sum this up, my total momentum before their interaction is mv plus 0, because this has a velocity of 0. So the total is mv. Well, afterwards, it's still going to be mv. So from that, I can say, well, I know what the final velocity is going to have to be, because after they collide, now I have basically 2m's worth of mass. And I know that the final momentum has to be mv. So that informs me that the velocity of this combined 2m mass has to be 1/2, because 2 times 1/2 is going to give me mv. So I can use this concept of it. I know what the final momentum has to be the same as the initial momentum. I can solve for the velocity. So I'll try again here. So I've got a 3m object at rest. And again, I have the same object, this mv1 hitting. But this time, instead of connecting to it and sticking, it's going to bounce off. So it hits it and it bounces off in the other direction. Well, here's what has to be true. The momentum beforehand was mv plus 0. So that gives me mv. The momentum afterwards has to be mv, by the way, in the positive direction. So if I look here, what I find is I have a 3m object traveling at 1/2 in the positive direction. So that's 1.5 in the positive direction. And I have an object of m traveling at 1/2 v in the negative direction. So I have 1/2 plus negative. I have 1.5 plus negative 0.5. I still have that same momentum that I started with. That's the idea here. Okay. So the form we generally take is this. So the problems we're usually faced with are something like this. We're told what the initial mass and velocity of the objects are, and we're told what the velocity of one of the objects is afterwards, and we're asked to solve for the final one. And the way we do it is we use the conservation of momentum equation, and we're just going to expand that. And just usually we have two object systems, so we're going to say m1 v1 plus m2 v2. That means object 1 and object 2 and their respective velocities is going to equal m1 v2, m1 v1, m2 v2 afterwards. So in other words, the sum of the momentum beforehand equals the sum of the momentum afterwards. So let's just look at this. I know it looks like a lot, but we're just going to go through it real quick. So let's just try this here. So I wanted to solve the problem I showed you. So I'm going to use m1v1 plus m2v2 equals m1v1 plus m2v2. We're going to use this a lot. So let's just substitute. Okay, so I've got 1 times 1 plus 2 times negative 1 is going to equal 1 times I don't know plus 2 times positive zero point 0.2. And I just solve for the velocity of this one. I'm going to find out it's going 1.4 in the negative direction. And that works because the total momentum I start with is the total momentum I end with. Now, there's a case that's worth noting, and that is often we have a situation where the two objects join together afterwards. Now, you could still use the other equation to solve it, but you can also make life a little bit easier by saying, well, since I know the m's are this, I know that the m's are joined together, and there's only one final velocity. It's a little bit easier to do it this way. So I say m1 plus v1, m1 plus v1, m1 v1 plus m2 v2 is going to equal the combined mass times this one final velocity. And so if I did the same thing I had before, I'd say, well, I know I have 1 times positive 1, 2 times negative 1 equals 3m times some unknown v. And when I solve it, I'm going to get negative 1/3. Okay? Which was different from what we had before. And last one, we'll try this one. So sometimes we'll have these kind of weird ones where like a bullet passes through a block of wood. For some reason, I really like these problems. I don't like guns. I don't like bullets, but I do like these kind of problems. So I have a 50 gram or 0.05 kilogram bullet is traveling to the right in the positive direction at 200 meters per second. I have a 1 kilogram block of wood that's traveling at 2 meters per second in the negative direction. Uh, and when that bullet comes back out of this, it's slowed down to 40 meters per second. So if you think about it, that this block is going to put a force on this one in the negative direction, and the bullet's going to put a force on this one in the positive direction. So if this bullet slowed down in this direction, it must have also slowed down or maybe reversed the direction of this one in the negative direction. Let's just see what happens, okay? So I'm just going to, since they didn't stick together, I'm going to use this form of the equation. And it's just a simple matter of substituting in, right? So I'm going to say 200 times 0.05 equals 2 kilograms times negative 2. You just got to keep your positives and negatives in mind here. Afterwards, I know that the bullet is still traveling in the positive direction at 40. And I want to find out what the velocity is of my 2 kilogram object. And when I solve this, I see I come up with a positive 2. So what that means is it was going this way at 2 meters per second, and afterwards it's going this way now at 2 meters per second. That's it, guys. Not so hard. We should have some fun lab work to do. Thanks for watching.